Rao Bhim Chapter 8, Eigenvalues, continued. In this chapter, we are not proceeding sequentially following the order of Rao Bhim. Instead, we are giving those things first which are more important. Now, we shall start with today's theme, which is how to compute eigenvalues easily for certain types of matrices. Theorem 8.2.5, if you start with a triangular matrix, A is a triangular matrix, then its characteristic polynomial is given by lambda minus aii, the diagonal entries, product of all those things. Let's see a quick example. Suppose we take an upper triangular matrix. An upper triangular matrix is one where all these elements are zeros. There may be zero entries here also, but if there is any non-zero entry, this must be in the upper triangular half, and we want to find out its characteristic polynomial. So what I do is I take lambda I minus this, which is this matrix. Now observe that this is also a triangular matrix. So when I want to compute its determinant to get the characteristic polynomial, I know the determinant of a triangular matrix is given by product of all the diagonal entries. So it will be lambda minus 5 times lambda minus 2 times lambda. The same argument proves the thing in general. Now we know that the roots of the characteristic polynomial are the eigenvalues. So immediately I get that the diagonal entries are the eigenvalues. So if I give you a triangular matrix, you can immediately say that the eigenvalues are its diagonal entries. Since diagonal matrices are also triangular matrices, it also follows that for any diagonal matrix, the diagonal entries are the eigenvalues. The next theorem along the same line of easily finding eigenvalues of a matrix is Theorem 8.2.7, but the book gives this theorem in terms of characteristic polynomials. I will first give an eigenvalue version of the same theorem, which is much easier to prove. Suppose I start with two matrices. One of them is m by n and the other is n by m. So I have sketched them like this. So in this picture I have taken m greater than n. Now I can make two square matrices out of them. One is A times B, which is m by m, and the other is B times A, which is n by n. There is an interesting relationship between the eigenvalues of these two matrices. Please understand that their orders are different. For example, the way I have sketched them, AB is a big square matrix, whereas BA is a small square matrix. The theorem says that these two matrices have the same non-zero eigenvalues. Thus, if a non-zero number is an eigenvalue here, it must be an eigenvalue here. If a non-zero number is an eigenvalue there, it must be an eigenvalue here. Now, before we prove it, the proof is quite simple. Let's take a look at an use of this result. Suppose we have this matrix, which is typically denoted by J, and is a quite useful matrix in statistics. It is a matrix consisting of all ones. It's a square matrix. In my example, I have taken it to be 4 by 4. I want you to compute all the eigenvalues of this matrix. Well, first observe that you can factorize this quite easily like this. You take the one vector, which is the vector of all ones, and multiply this with the same vector lying horizontally. So you can convince quite easily that this is that matrix. So it is like A times B. Now what I will do is, I know that all the non-zero eigenvalues of this must be same as the non-zero eigenvalues of the same two matrices multiplied in the reverse direction. Now this is quite easy, right? Because this is 1, 1, 1, 1 and then 1, 1, 1, 1, which is simply the number 4. So it is a 1 by 1 matrix. Now if it is a 1 by 1 matrix, its eigenvalue is itself. You can see that quite directly. You can think of it as a diagonal matrix of size 1 by 1, or you can just directly put it inside the definition. So you can see that for a 1 by 1 matrix, the eigenvalue is itself. So I immediately know that this has only one eigenvalue, which is 4, and that is a non-zero eigenvalue. So 4 must also be an eigenvalue here. Not only that, 4 must be the only non-zero eigenvalue. Now here we have a 4 by 4 matrix, so it has got 4 eigenvalues in C. So the other 3 eigenvalues must be 0, because the non-zero eigenvalues are all shared. So we must have the eigenvalues are 4, 0, 0, 0. 4, 0, 0, 0. So very easily we can compute the eigenvalues of the matrix J. Now to prove this, we assume that suppose lambda is a non-zero eigenvalue of AB, so I take lambda not equal to 0. And since it's an eigenvector, so I also take V not equal to 0. So this is what is meant by saying lambda is an eigenvalue of the matrix AB. I want to show that this lambda must be an eigenvalue of BA also. Well, all that I do is pre-multiply this by B both sides. So I have this. So now I can write it as BA times BV is equal to lambda times BV. So BA times a vector is lambda times the same vector. So this looks very much like the eigenvalue definition. So lambda does look like an eigenvalue of BA, except that we need to check this is a non-zero vector. Now I had V non-zero, that does not mean that BV has to be non-zero, but can BV be 0? If BV is 0, then what will you have here? This is 0, so BV, so initially I started with just AB equal to lambda V. Now if you say BV is 0, that will mean that this will be the 0 vector. So lambda V will be equal to the 0 vector. But V is non-zero, so that will force lambda to be equal to 0. But I said lambda is non-zero. So BV cannot be equal to 0. And immediately we get that lambda is an eigenvalue of BA. Not only that, we also get as a bonus one eigenvector for lambda for the matrix BA. Now we come to theorem 8.2.7 as given in the book, which I call the characteristic polynomial version. I again start with two matrices, M by N and N by M. Now without loss of generality, but for sake of statement, I will assume that M is less than or equal to N. I consider these two characteristic polynomials, one for BA and the other for AB, and there is an interesting relationship between them. First, understand that this is an N by N matrix. So this is a monic polynomial of degree N, and this one is a monic polynomial of degree M, and I have assumed M is less than or equal to N. So I have to multiply with certain polynomial of degree N minus M, and that certain polynomial turns out to be super simple. It is just lambda to the power N minus M. So once you have this result, the eigenvalue version follows immediately from this, because if there is any non-zero root here, it must come from this part, and that will be here also, because this will contribute only root 0, N minus M many 0 roots. Now this is stronger than the last theorem in the sense that here you can see that the non-zero eigenvalues occur with the same algebraic multiplicity. So if I have some lambda naught which is an eigenvalue of BA and lambda naught is non-zero, in that case the algebraic multiplicity of lambda naught for BA must be equal to algebraic multiplicity of the same lambda naught with respect to AB. So that is a stronger result that we get here. Now the proof as given in the book is pretty long and complicated and uses certain other things which are not directly related to understanding eigenvalues, so I shall skip the proof for the time being. Suppose I start with the square matrix A and some eigenvalue lambda of A. Now I will pre-multiply both sides by A, so I will get A square here, A square V equal to lambda AV, lambda being a scalar, comes out of the multiplication. So from this I can see something interesting. Namely, this AV is again lambda V, so it is lambda square V. Remember, V was non-zero, so A square V equal to lambda square V is again like the definition of eigenvalue and eigenvector. So we see that lambda square must be an eigenvalue of A square. Clearly, if I multiply it with A cube, that is multiply with A square, it will just proceed in the same way, and I will be left with lambda cube here. As a result, if I take any power n, then that has an eigenvalue lambda to the power n. Now suppose I start with this again, but this time I multiply this with 2, so the 2 comes here, so you can say 2a has an eigenvalue twice lambda, and all along I am still working with the same eigenvector. Okay. Now suppose I do something even stronger. Suppose I now work with a plus a square. What can I say about that? So I will a plus a square and I multiply by v. Well, I will just distribute. I get av, which is lambda v, and I take a square v, which is lambda square v. As I am working with the same v, I can write it as lambda plus lambda square v, which means lambda plus lambda square is an eigenvalue of a plus a square, and this immediately motivates theorem 8.3.3. We start with a polynomial, some polynomial f, and lambda is some eigenvalue of a matrix A. In that case, f of lambda is an eigenvalue of f of A, not only that, corresponding to same eigenvector. Now, let's clearly understand what is meant by a polynomial in A. So, suppose I take fx equal to 5x square minus 6x plus 37, then by fa, I will understand 5a square minus 6a. Now comes the problem. I cannot add a constant 37 to a matrix. I interpret this as 37i. So this is the matrix which I call f of A, and this has that corresponding polynomial of lambda as eigenvalue. Now proof is exactly the way we did. Just remember, this addition of I causes no problem, so I will just give you a simple example. Suppose you have got a plus I. So your polynomial here is x plus 1. Now multiply this with v from the right. So this was an eigenvector of a corresponding to lambda. Then you will be left with a times v, which is lambda v, and then v times I, which is just v itself. So that is equal to lambda plus 1 v. So you can see that lambda plus 1 acts as an eigenvalue of a plus I. So the rest of the proof is just trivial now. This theorem has an immediate corollary that if A is idempotent, that is, if A square is equal to A, then the eigenvalues of A must be 0 and 1, because I have got A square minus A equal to 0. So whatever are the eigenvalues of this, so this is equal to 0. So if I take lambda to be an eigenvalue of A, then lambda square minus lambda must be eigenvalue of the 0 matrix, and you can easily see that the eigenvalues of the 0 matrix must be all 0. So this must be equal to 0, which basically means that lambda is either 0 or 1. Now of course we can have an idempotent matrix where 0 is not an eigenvalue at all, only 1 is eigenvalue, and such a matrix is unique, that is just the identity matrix. Or it could be that all the eigenvalues are 0, 1 is not an eigenvalue, that one such matrix will be just the 0 matrix, and all other matrices may have a mixture of 1 and 0s. We saw that if A has an eigenvalue lambda, then A to the power n has an eigenvalue lambda to the power n, where n is any number in 0, 1, 2, etc., where A to the power 0 is defined to be identity matrix. Now my question is, what happens if I put n equal to -1? Is it true that A inverse must have an eigenvalue which is reciprocal of lambda? Now, in order for me to talk about A inverse, A must be non-singular. Okay, I give you this. Suppose A is non-singular. Then is it true that this is true? Yes, it is indeed true. That is quite easily seen, because if I take the defining equation AV equal to lambda V, where V is non-zero, just pre-multiply by A inverse and you will immediately see that this is A inverse this and this is A inverse, which means A inverse V equal to, bring the lambda here, they cancel off, 1 over lambda V. So you have this result. Now you might be wondering, how could I divide by lambda? How do I know that lambda has to be non-zero? So I only assume that this is non-singular. I did not assume separately that lambda is non-zero. Well, that is not a problem, because lambda can be 0 if and only if A is a singular matrix. That is pretty straightforward, because remember that lambda is such a number such that lambda I minus A is a singular matrix. That is indeed how we computed eigenvalues. Now, if lambda 0 satisfies that condition, this will mean that minus A is a singular matrix, which means A is a singular matrix, but I assume that A is non-singular. So that also gives us a pretty useful result. A matrix A is non-singular if and only if all its eigenvalues are non-zero. Even if there is at least one zero eigenvalue, you can say A is singular. Suppose A is a matrix and lambda is an eigenvalue and f is some polynomial, then you have just now seen that if I consider fa, then fa has an eigenvalue f lambda. Now the natural question comes that what can I say about its algebraic multiplicity above? So suppose I know that lambda occurs with algebraic multiplicity 5. Can I say that f lambda will occur with algebraic multiplicity 5 for fa? Well, not necessarily. However, there is something that we can say. What we can say is this: suppose all the eigenvalues of A are lambda 1 ... up to lambda n. Now when I say that these are all the things, I am taking n by n, I mean that they may be repeated. In other words, these are all the n roots of its characteristic polynomial over the complex field. So there may be certain things which are repeated. For example, if my characteristic polynomial happens to be lambda minus 2 square lambda minus 3 cube, in that case I can take them like 2, 2, 3, 3, 3. So I will say I have got 5 eigenvalues. They are all listed here. 2 is listed twice according to algebraic multiplicity. 3 is listed thrice. In that case, we can say something interesting, namely, all the eigenvalues of fa will be precisely f lambda 1 to f lambda n. Now, since this f need not be a one-to-one function, so it is quite possible that two things which were distinct here now get mapped to the same thing. For example, if I have something like lambda minus 1 and I have got lambda plus 1, then my eigenvalues will be 2 1s and 3 minus 1s. 2 1s and 3 minus 1s. Now suppose I take my polynomial, which is just squaring fx equal to x squared, then everything will be mapped to 1 1 1 1 1. So the algebraic multiplicity of the eigenvector 1 will not be 2 anymore, it will be 5. That is why I said that the algebraic multiplicities do not translate immediately here, but they do once you take into account the nature of the polynomial. Now this result, the fact that if lambda 1 to lambda n are all the eigenvalues counted according to algebraic multiplicity, will translate nicely even after you take the polynomial transform, will require some further machinery to prove. So we are postponing the proof for now.